Hello everyone, welcome back to Math with Allison. Today we're going to be working in our integration series, so we're going to be talking about related rates. So acceleration, velocity, and position. So let's go ahead and dive into it. We're going to remember how we can find these using the derivatives. So first we have position is usually what we start off with. So this is just equal to s of t. Why did we label it with s? I don't know. In order to find the velocity, though, we would want to take the derivative of our position. So here we get velocity is equal to the first derivative of the position. It represents the rate of change of the position. And so for that very similar reason, acceleration is equal to the second derivative of our position, or we can rewrite that as the first derivative of the velocity. So now we can go ahead and work backwards. So usually what we do is start off with acceleration, which is equal to a of t, right? So in order to get velocity, we're actually going to integrate our acceleration in terms of time. And now in order to get to position, we're going to integrate velocity in terms of time. So I have a little chart for us right here. And when we are wanting to take the derivative, we go down the chart. We go from position, velocity, acceleration, because derivatives represent all those rate of change. Now when we go backwards, we're going to integrate. So we start at acceleration and we can go upwards. We can go to velocity, we can go to position. So that's how it works with related rates. And we're going to go ahead and see an example here. So we have runner A begins at the point s of 0 equals 0. So their starting position at time equals 0 is 0. And they run a straight line on a level road with velocity v of t is equal to 2 times t. Runner B begins with a head start at the point s of 0 equals 8. So at time equals 0, they start, 8 meters ahead? And they run with a velocity of v of t equals 2. So find the positions of the runners for time is greater than or equal to 0 and determine who is ahead at 6 minutes. Let's go ahead and talk about runner A, and let's write down their important information. The first thing is that they start at 0 at 0. And we also have that their velocity is equal to 2t. So we want to go ahead and find the position equation for this runner. So in order to get to position, s of t, we need to go ahead and integrate our velocity function in terms of time. So when we plug that in, we're going to go ahead and integrate 2t dt. So when we do that, we're going to go ahead and use a power rule. So we add 1 to the exponent and we divide by that new exponent, but we have to add on some constant c, right? So notice here we can just simplify this down to t squared plus c. And we are almost done with our position function. The reason I say almost is because we need to figure out what that c is. And we're going to do that by using the initial value. So here we have s of 0 equals 0. So that means I'm going to set 0 equal to, and I'm going to plug in 0 to our equation. And here we get our c value is equal to 0. So that means we can find our final equation, and we have s of t is equal to t squared plus 0, or I'm just going to leave that as t squared. So here we have runner A. Let's go ahead and find runner B. Let's write down their important pieces of information. We have s at 0, so their starting position is equal to 8. And we also have their velocity function is just equal to 2. So again, we're going to go ahead and find the position by integrating the velocity, 2 in terms of time. So when we integrate a constant, we're just adding on a value of t. So we get 2 times t plus some constant c. So now we can go ahead and use this initial position in order to find what that c value is equal to. So we know s of 0 is equal to 8. So we have 8 is equal to 2 times 0 plus c. Here we get 8 is equal to c, and we can get our final equation, s of t is equal to 2t plus 8. So now we have both of their equations. I'm going to go ahead and highlight them. And we want to go ahead and compare who is ahead at the time 6. So let's go ahead and plug in those values. I'm going to do it on the other side over here. So we have s of 6 for our first runner is equal to 6 squared, which is equal to 36. Now for our second runner, we got s of 6 is equal to 2 times 6 plus 8, which is equal to 12 plus 8, which is equal to 20. So here we can see that runner A is ahead. Okay, so let's go ahead and take a look at the graphs in order to see how this is happening. So here we have runner A, and we can see their velocity function, which was equal to 2t, right? And so here we have that in red, and then we have their position function, which is equal to t squared. So here we have the velocity still represents the rate of change. We just were able to work backwards. So that checks out for us. And then here we also have runner B. in which we have our velocity was just equal to a value of 2, which is going to be a constant straight line. But our position was equal to 2t plus 8. So here we have a starting value of 8, and we can see that we're going to increase by a slope of 2 over 1 each time, which is represented with our velocity. We're increasing by 2 every time. So it looks like those check out, and we also can compare the position graphs to see who was further along. So here we have both of those mapped up. We have the runner A, and we also have runner B. So when time is equal to 6 minutes, we can see that's highlighted right there. We can see that runner A is going to be much further along than runner B, and that's because they're running at a quadratic type of function, and runner B is running at a linear type of function. So here we're seeing which grows faster. Let's go ahead and try another problem. So here we have ignoring air resistance, which we like to do. The motion of an object moving vertically near Earth's surface is determined by the acceleration due to gravity, which is approximately 9.8 meters per second squared. Suppose a stone is thrown vertically upward at t equals 0 with a velocity or an initial velocity of 40 meters per second from the edge of a cliff that is 100 meters above a river. So let's go ahead and draw a picture of what this person is doing. Here we have a cliff, right? There's our wonderful cliff. And then at the bottom of the cliff, we have a wonderful river. I should be an artist, guys. So somebody is standing up here and they go ahead and throw a stone. So here we have a distance of 100 meters, and they're throwing a stone at 40 meters per second. So the stone is going to do something like this. It's going to go upwards, and then it's going to hit a maximum, and then it's going to go downwards, and it's going to go straight into the river, theoretically, if they threw it perfectly. So let's go ahead and go through this problem. So first we want to find the velocity of the object for t is greater than or equal to 0, because we don't work with negative time, right? So that's just in terms of the context. So in order to find the velocity, we want to go ahead and take the integral or the antiderivative of acceleration in terms of time. So in this case, our acceleration is going to be 9.8, but I want us to notice something. Typically, when we think of positive, we think of going up. And when we think of negative, we think of going down. Gravity is pushing downwards on us. It is holding us to Earth. It is pushing the rock downwards, which means acceleration is going to be negative. So here we're integrating negative 9.8. So just like earlier, when we integrate a constant, we get negative 9.8 t plus some value c. So we can actually find what the c value is equal to just like last time, and we're going to do that using the initial velocity, which we have right here. So at t equals 0, velocity is 40. So here we have velocity is 40, and we can plug in that value of t being 0. And here we get 40 is equal to c. So let's go ahead and plug that into our velocity function. We have v of t is equal to negative 9.8 times time plus 40. So here we have our velocity function. So let's go ahead and look at the graph. Here we had acceleration, which is a constant negative 9.8 meters per second squared. And now we have our velocity. So our starting velocity is right up here at 40. So at first our velocity is positive because the rock is being thrown upwards. So here we can see as it's above the x-axis, we have a positive velocity, which means the stone is moving upwards. But very quickly we hit a value of 0, which means the velocity of the stone is going to be 0. It's not moving at all, which is going to be at the apex right here of its position. So here it hit the apex, and then we flip to a negative velocity. And so this is going to be where the stone is moving downwards. So that's how we can read the velocity graph. And the acceleration shows the rate of change, which is going to be the slope of our function. If we use change in y over change in x, that's going to be negative 9.8. So that's the graph, and let's go ahead and move on to part B. We want to now find the position function of the object for t is greater than or equal to 0. So I'm going to rewrite our velocity. And in order to find position s of t, here we're going to go ahead and integrate negative 9.8 t plus 40, all in terms of time. So when we do that, we end up getting negative 9.8, and we add 1 to the exponent, divide by that new exponent, plus 40t plus some constant c. So if I write this out nicely, we have s of t is equal to, that becomes negative 4.9 t squared plus 40t plus c. So now let's go ahead and find c. Let's go ahead and look at what the original problem was saying, and we want to look for a position of some kind. And it's going to be right here. We're throwing from the edge of a cliff that is 100 meters above the river. So here that tells me our position is going to be 100 meters when our time is 0. So when it's initially thrown. So here, those are both being multiplied by 0. We get 100 is equal to c, which tells us our official position function. We get s of t is equal to negative 4.9 t squared plus 40t plus 100. I'm going to go ahead and highlight that. So let's go ahead and take a look at the graph. So now we have them put all together. We have acceleration, which was the gravity. This is negative 9.8 meters per second. Then we move up to our velocity, and our velocity was negative 9.8 t plus 40. And then we also have our position. This was equal to negative 4.9 t squared plus 40 t plus 100. And so this represents the actual position of the stone being thrown. Okay, so let's think about concavity first. We know that this is going to be concave down because the second derivative of it is equal to negative 9.8. The second derivative is a negative value, which tells us it's concave down the entire time. Now, the first derivative, which is going to be velocity, the first derivative tells us if our function is increasing or decreasing. So first we have that our velocity, or our first derivative, is positive. It's above the x-axis, and so we can see that our position function is increasing. Then we hit a value of 0, which shows the apex of our actual position. Then our function switches over to being below the x-axis, which means it's negative, and our function is decreasing. So that's how these all work together. So our next step is to find the maximum height of the object. So if we look back on our graph, the maximum height is going to occur at the apex of our function, which we need to know what time that's happening at. So the x-axis represents the time, right? And that's going to occur when our velocity function, I did not draw a straight line, is equal to 0. So what we're going to go ahead and do is we're going to take our velocity, and we were going to set it equal to 0 because we're looking for a critical value, right? We're looking for that local maximum. So let's go ahead and solve. And I'm going to divide both sides by negative 9.8. And here we get t is equal to 4.1 seconds. So now that we have time, we can plug that back into our position. So s of 4.1, that is going to give us our height right here. And let's go ahead and plug that in. Okay, I definitely plugged this into a calculator. I got 181.631 meters. And so this is going to be the total maximum height that we reach. And if we look at our graph right here, we can see it's a bit more than 150, so we get 181-ish. Okay, and then part D, with what speed does the object strike the river? So this is going to be when it actually hits the river. And we want to think about the time in which it's hitting the river. So in order to find when we're hitting the river, we want to see where our position function is equal to 0. So it's like we're finding the zeros of it. So I'm going to go ahead and take our position function. And I'm going to set it equal to 0 in order to solve for the time. So here I definitely plugged it into a calculator. Again, we got negative 2.0067. And we also got t is equal to 10.17. So let's go ahead and think about the context. We're working with time. We're throwing a stone. So in real life, we don't have negative time, right? So we get to ignore that value, and we're just going to focus on t equals 10.17. So we're finding the speed in which the stone hits the river. So speed has to do with velocity. So I'm going to go ahead and take our velocity function, and I'm going to plug in our time. So we got our velocity is equal to negative 59.67, and that's because the stone is coming back at the earth. So it's going in a negative position. So it's going in a negative direction. But this is specifically asking for the speed, and the speed is never going to be a negative value. So we want to take the absolute value of it. So that's a nice little equation for us. We just take the absolute value. So here we get the absolute value of negative 59.67, which is equal to positive 59.67. And here we have the speed at which the object strikes the river. So that is all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.